this is not the scan code. Just like, I mean, my screen is kind of like today's lecture, but for some reason that doesn't show that. Okay. This is what it's supposed to show, if it shows. Huh. Oh, it's okay. Let's see if it says here. Okay, I have the attendance slide on the left, so let's start with the lecture. Okay, 9:31 a.m. So I'm going to start the lecture. So now we are on lecture 21. So we have like so many lectures so far. Any questions so far about anything, any part of the class, or naming compounds, alkanes, alkenes, alkynes? Everything's clear? Okay, so I posted the homework on Saturday because I realized it's more feasible that I first post 275 homework than my 101 because I'm writing so many versions for those students. And as I said, for this class, I'm more comfortable, and I expect you guys to just follow my instructions. So as long as I feel like it's not needed to have multiple versions, I just have one version. Okay, so if no question from previous lectures or the class and all that, and the deadline for the homework is this Wednesday. And I had some students asking me about midterm. So as you notice, we don't have the traditional midterm exam, but I feel like you have enough homework, quizzes, and exams that I don't want to add another exam before your break. So just do the homework, and I post the quiz. I try to post it on Wednesday, but I might post it on Thursday. But you see the structure of the quiz that when you start it, you should finish it. So just I advise you to just take more time to study the materials and then take the quiz. Any questions? Okay. So yeah, that's that. Now, first I start with the practice example from previous lecture, and after that I have another example for something that we talked about last session, and then I talk about new materials. But before I just throw the solution to you guys, I asked you to just work on this problem for 1 or 2 minutes to see if you can answer the question, and then detect what is the issue or what part you're struggling with, and then I can explain in more detail about that part, right? So the question asks, which of the following compounds can exist as cis-trans isomers? And that can be a question from your quiz or your homework, right? So how would you solve the problem? Probably you first draw the structures, right? Because when we have cis-trans isomers, what is specific about those? Specifically in alkenes. Anyone?
The substituents are on different sides.
Exactly, on different sides of the double bond, exactly. So is everyone comfortable with writing the structural formulas of these? Okay. So I just want to emphasize and add some points about cis-trans isomers. So in order for us to have cis-trans isomers in alkanes, when we have double bonds, first of all, we should not be able to get the structure when we rotate it, right? So do you remember that when we had double bonds, rotation was restricted? Do you remember that table that I listed in the last class, right? So if you draw a structure and easily you can get the other structure, and with the next slide you know what I mean, we won't be having cis and trans isomers. So first criteria is that the rotation must be restricted in the molecule. The second is that there must be two non-identical groups on each doubly bonded carbon atom. So if you have like carbon double bonds and then you have like two CLs, you know, if you have like two, you know, you should have like, you know, if you have like two CLs that are identical attached to each of these carbons, we won't be having cis and trans. So we should have, for instance, Cl and CH3, for instance, or like Cl and Br. Any questions? And remember, we should have like two non-identical groups on each side of the double bond, right? We need here that rotation must be restricted and we should have two non-identical groups. So now going back to the example, kind of like to be faster with the lecture, I have like all these structures here that I asked you here, right? So here we have like propene. So we have like 3 hydrogens, and we don't consider hydrogens as being like branches. Remember, we consider like Cl, Br, methyl, ethyl, those ones, right? So for that matter, when we only have like one CH3, this molecule itself, propene, cannot have cis and trans. Because, so for instance here, for 3-hexene, if you write the structures, you can have like, so here, for instance, for cis, and again remember, for here we have like the both CH2, CH3, and then CH3, CH2. Both of them are on one side, and then here they are like on different sides, right? So here it would be trans, this one would be cis. And when we're writing hexene, you can draw either of these structures and still you have like 3-hexene. Yes?
So even though they have the same like actually like different molecules, it's still different because of the arrangement of them?
Exactly.
Because the two non-identical still needs to apply, right?
Exactly.
Okay.
Yes. So if you had like, for instance, hydrogen here for both of them, or like, you know, in that case, they would be like identical, so it wouldn't be like distinct.
Okay, but since they are just kind of switched structurally, it still works? Okay.
Exactly. And do you remember what type of isomers these are? Is it conformational, constitutional, configurational? Configurational. Exactly. Okay? Those are stereoisomers. So what about 2-methyl 2-butene? Can we have cis and trans here? Do we have the criteria? Do we have this criteria here? No, right? We have like CH3 on each side, and here we have like the carbons on double bonds, and so we cannot have like cis and trans. Okay? So what about ethene? Can we have cis and trans here? No. Okay, so is this example clear? Any questions? Okay, now let's do another example. So write an equation for the reaction of bromine at room temperature with 4-methyl cyclohexene. So can you guys quickly draw 4-methyl cyclohexene? So what is the first thing you do? We have like, so we see the word, first of all, hexene, and we see like cyclo, so we know we have a ring that it should have like 1, 2, 3, 4, 5, 6 edges, right? And then we have hexene, so we know that we have like 1 double bond, right? Can anyone tell me why I don't have 2 double bonds?
Because it would make it a hexadiene.
Exactly, right? Remember, we use like di when we have like 2 double bonds, so we add like diene, or like triene, or like tetraene, kind of, if you think of it like that. Okay, so now we have like 4 methyl. It says that, you start counting the carbons on double bond, and then if you start counting here, you cannot go this direction because you should encounter the other side of double bond. Does that make sense? So if you start here, you have to go this way because we name both carbons that are in the double bond. Does that make sense? So we don't go this way. We say 1, 2, 3, 4. And then we have like a methyl group here. Okay? So now we want to react that with bromine. And you know that bromine is a molecular element, right? So it would be Br2. So here I have like the structure written for you. And when we want to react that with Br2, what type of reaction is this? So for those of you that say substitution, what did Br or Br2 substituted with? So let's see. So if this is like, and maybe I can just like do it here. If we have like carbons here, how many hydrogens do I have here? Here. 2, right? How many here? 1. How many here? What about here? Here. Here. Okay. Now, if I want to substitute this, I want to give a good reason why we didn't substitute here, but now that I think about it, you can just like. So when we have like alkenes, what happens is that because the sigma, so you know that when we have double bond, we have like just between carbon and carbon. And this is the thing, remember when I asked you in your like homeworks or quizzes or something, when I asked how many sigma or how many pi bonds I have in a molecule, you should notice what I'm exactly asking. Am I asking about like the whole molecule or just between the specific elements? So here, between like this carbon and carbon, what bonds do I have specifically? So I have a double bond, but each of them, how many sigma, how many pi bonds do I have?
1 sigma, 2, and 1 pi bond?
Yes, so I have like, I have 2 bonds overall. So one of them is sigma, the other one is pi bond. And for these type of reactions, when we have like a halogen, what happens is that the pi bond will be broken because it's more unstable compared to the sigma, and my double bond turns to a single bond. Okay, so if we agree that this is what happens, now what type of reaction do you think we have? So now we just have like a single bond here. This double bond will be broken. Now I have only a single bond. So if we agree that's the case, now what type of reaction do I have? Addition, right? I was trying to just, explain here that why just not like we have like one hydrogen being substituted with bromine, but I needed like more explanation about like bonding, and then you should know that this pi bond will be broken. We have like only one sigma bond now, and that's why we have these Br atoms right now being added here. And the only way that you can add that, you should break one bond. It's not possible that have it with like double bond. Yeah.
How do you know that that bond right there has one pi and one sigma? Is that just...
This is how double bonds are.
Okay.
So when we have only one bond between the atoms, that should be necessarily sigma bond, because sigma bond is much more stable than pi bond.
Okay, so if you have two, then it would just be one of both. So what would a triple bond be?
So it would be one sigma two
Okay.
pi bonds.
Cool, thank you.
Yeah. And these are like the things that chemists study, and they realize, okay, in alkenes we have like one sigma, one pi. So for each molecule is different. But this is how it is for alkenes. Great question. Any other questions? Okay. So now that the double bond here is broken and now we have like a single bond, here is where you should add bromine atoms. So you wouldn't add anywhere else, because here now you have like, room for two more bonds. Okay, so for alkenes, when you want to react them with halogens, you break the double-double bond, you have like one single bond, and then you add the two halogens in each side of the double bond. Any questions? Are we good with this? Okay, now we're going to start today's lecture and talk about like the other type of addition reactions. So one type was like with halogens, this type is with water. And water, as you all know, is H2O, right? And you can write this H2O as like HO basically, so this is H2, right? So basically it can be like H and HO or OH, right? So if you think of water as HOH, this is kind of like similar to what we learned before. And now, instead of having like two Cl atoms or like two Br atoms, you have like one H, one OH, okay? And in order for this reaction to proceed, we should have an acid catalyst. And we briefly talked about catalysts. Can anyone remember the definition of a catalyst? What is it?
Speeds up a reaction.
Yes, exactly. So it's a substance that accelerates the reaction, but it doesn't being consumed, or it doesn't react with your reactants or products. It just accelerates the reaction. That's why we just write it in the arrow here. And don't get that confused with the previous, previously when we had like the substitution reactions, we could write like, for instance, the Cl2 in the arrow to be like much faster, right? So this one is different. This is like your catalyst, and you don't attach that to any of your reactants or your products. You just write that to know that this reaction occurs in the presence of a catalyst. If not, this reaction won't occur, okay? So now, here again, we do the same thing. You break one of the double bonds, basically the pi bond, and then you have like just single bond between the two, carbons. And what you do, you add one H to one carbon, one OH to the other carbon. And do you remember that when we had like OH in a substance, what type of substance that would be? Does any of you know? It would be one type of alcohol. Okay? So for instance, CH3, CH2OH, or like this, So So this is, oh, so this is not CH3, this is like C2H. Oh yes, sorry, yeah. So basically CH3, CH2OH, or you can write this if you just count the number of atoms, it would be C2H5OH, right? You can just denote them however you want. So remember, this is like the abbreviated structural formula. This is just like the molecular formula. This is kind of like more basic expanded structural formula. So if you see any of those, you should be able to distinguish what the compound is. And we call that ethanol. And it's one type of alcohol. Any question so far? So basically, if you have like alkene plus, or maybe I can just like erase this so I have more room. If you have like alkene plus water in the presence of acid catalyst, you will get alcohol. You can get ethanol, depending on how many carbons you have. This is how you name them, it's like etha, or like methanol, ethanol, propanol, and then you add like NOL to name alcohols. Any questions? Is this clear? And now we can have like anything that we talked about for like these, alkenes here, you can have like with cycloalkenes as well, right? So here we have like cyclohexene, and remember that if you only have like one double bond and you don't have any substituent, you don't have to use 1, 2, or like numbers in general, because all of them are like equivalent, right? So now if I add water, again, we denote that as like HOH, so it would be more straightforward for us to write. So what happens, again, you break this double bond, you convert it to like a single bond, and then in one of the carbons you add hydrogen, in the other one you add OH. Okay? And you call this cyclohexanol. Because again, OL, or like NOL, or like OL itself, alcohol, so OL. This is because of like the being an alcohol, and then cyclo because you have a ring, and then hexa because you have like 6 carbons in your ring. Okay? Any questions? Good. Very good. So addition of water, we call that hydration, because we're basically adding water. So remember that hydration is addition of water. So I give you guys 1 or 2 minutes to write this equation, and then I'll show you the answer. And I encourage you to write it to see where is the issue, or like what part you're struggling with, so I can explain that to you.
Do you want us to draw structure or like equation?
Whichever you're more comfortable with. Usually if you write the structural formula, it's like more easier to substitute things, so more straightforward, but you don't have to. here I didn't. Okay. Did everyone draw 4-methylcyclopentene? Any questions about this structure? So when you see these questions in the exam, just pay attention, you know, that you have pentene, you have like cyclopentene, the methyl group is like in the carbon number 4. And again, remember, when you start counting from, for instance, here, you should necessarily count this direction, okay? You should count the both carbons in double bond, yes.
So, you didn't write the extra hydrogen because it's just not necessary to write it? Like you had the OH and then the hydrogen you didn't branch. Is that just because?
So you can write it or not write it, because if I don't write here the hydrogen, so it implies that I have carbon and how many hydrogens attached to it? Two, exactly.
Right, and before it was only one.
Exactly. Before this carbon here, it had like 1, 2, 3, so it was just like 1.
Okay.
So you can write it to emphasize, but if you don't write it, it also, you know, implies that it has another hydrogen here, and then you have like the OH here. And remember, you add the hydrogen, OH, or like if you have like chlorine atoms, you always add them to the so-called double bond, you know. So now it's like single bond because we broke the double bond, but you add them to these carbons. So what I'll do in your quiz, I put like bromine here, or like, you know, OH here. You see here? It's like, it just have like, you know, make a small change. So here, for instance, or here, and you should know that you add them to the previously double bond that you now converted to a single bond, because now this one has like room for like H and OH. Are we good with this? Hydration. And
Double bond? Does it matter if you add it to first and second?
so it doesn't matter, we can add it to either. Yeah. As long as you add it to both, you're good. Great question. Any other question? Good. The other thing that I explicitly, okay, and talked about it, but here it is. Now we want to talk about addition of acids. And as you see, all of these things are just like following the same pattern. So if you learn one of them well, now the rest is pretty similar. And here, for instance, you have like, again, when we don't have anything, we have like hydrogens here, like C2H4. What is the name of this compound? Ethene, right? It was listed here too. So anyway, so now we have like hydrogen chloride, or like in general, if you have like the generic formula, it would be like HA. And don't get confused, you know. So when I have like HA, A can be any other atom that forms an acid, right? So we use that HA in general to denote that. And do you remember, based on like previous, you know, Chem 101 or like other chemistry courses that you had, that when we have like binary acids, we write like hydrogen, base name of the non-metal, and then plus IDE, like hydrogen chloride, hydrogen bromide. So, and one of them here, for instance, hydrogen, it has like partial positive charge, and then the other atom has partial negative charge. And then if you learn the oxidation states, well, here it helps you to find like the oxidation states, and then know which atom has like partial positive, which atom has like partial negative charge. But you can also remember that hydrogen in acid, in binary acids, has partial positive, and then the other atom has like partial negative charge. And we do the same thing. This double bond, you convert that to a single bond, and then you add like hydrogen to one carbon and the other atom of your acid to the other carbon. So for instance, if you have like ethene and hydrogen chloride, you add like this chlorine here and this hydrogen here, and you can like switch them too. You know, Cl would be attached to this one, and then, you know, so basically, as long as you attach one hydrogen to one carbon, one Cl to the other carbon, you will be all fine. And we call that chloroethane or ethyl chloride. We didn't talk about common names much in this class, and when it comes to the naming, I asked you naming, IUPAC namings that we talked about, okay? So, but it's good for you to know that the other name of chloroethane is ethyl chloride, but I don't ask you common names in the exam. So as long as you know the IUPAC names that we thoroughly discussed in the class, you'll be good, but I encourage you to know the common names too, so when you see a compound, you can recognize what they are, okay? Any questions so far? So here is another example. So we have like cyclopentene, right? And then now we want to react that with sulfuric acid. So you remember sulfuric acid is H2SO4. But again, for the sake of for us to be able to write these addition reactions, it's always like good to have like one hydrogen separated, so you know that one hydrogen. So first of all, you break this double-double bond, you have like single bond, and then you attach one hydrogen to one carbon of the former double bond, and the other, anything is left, which is here OS, O3H to the other carbon. And we call this structure cyclopentyl hydrogen sulfate. Again, you don't have to worry too much about the names. So I asked you in the exam, IUPAC names that we talked about in the class, and I think those would be like enough for me to ask you. But I encourage you to know kind of like these names too, so you know that. Any questions? And for these types of reactions that we add acid to an alkane, it would be whether binary acids, which is like HF, HCl, HBr, HI, those types, or sulfuric acid, which is like here, and we have like one example here. So. Good? Yes?
These don't need a catalyst reaction because you're adding an acid, right?
Yes.
Okay.
Yeah.
Because the other ones you had to add the acid as
Yes,
a catalyst.
so exactly, because water, so some people say, so water is basically amphoteric, which is like has both acidic and basic characteristics, but since you know it's basically not a strong acid or not a strong base, that's why we call them amphoteric. So for that matter, it's not like it doesn't have enough acidic character for the reaction to occur by itself.
Okay.
Yeah.
Thank you.
Great question. Yes.
Why is it cyclopentyl? Why isn't it pentane?
Because when you have like the, you know, this when you add the acid to the structure, the name does not follow the rules that we learned before exactly. So although it only has single bonds, now we don't call it, at least like with this naming system, you know. So cyclopentyl. So yeah, most of these compounds that have like several names, so it probably has an equivalent IUPAC name as well, but we didn't talk about that in the class. So yeah, great question. Any other questions? Okay, now I'm going to kind of like, I mean, still we're going to talk about reactions, but not specifically, you know, like addition reactions that we were talking about. So now I'm going to go to section 311, and next class I'll go back to the previous sections that I missed, but I thought it would be good to just kind of like change the subject a little, so we have like more, you know, diversity in the topics that we talk about, I guess. So Does anyone know what is a reaction equilibrium? Or have you ever heard of it? So what is it?
Is it kind of when a reaction kind of go back and forth both ways?
Exactly. So if we have like most of the reactions, or I think all of the reactions that we talked about in this class, they were like going from reactants to products, right? We didn't have like these double two-sided arrows, right? But most of the reaction can proceed in both directions, meaning that if you have like your reactants and they form the products, now your products can also mix with each other, react with each other rather, and then form your reactants. And if we have like no reaction between them occurring anymore, meaning that your reactants turn to products and then your products generated the reactants again, and if at some point the reaction doesn't proceed in either direction, and then you have like the same concentration of each of your reactants and products. In that case, we say that the reaction reached an equilibrium. It means that it's not proceeding in either direction. Does that make sense? But in general, as we just mentioned, most of the reaction, and if you have like a reaction that only has like arrow to one side, it means that it wouldn't progress to the other side. But if you have like arrows on both sides, or you can write it like this for like brevity, it means that not only your reactants produce products, now your products also react and then produce reactants again. Okay, and then we should have some quantity to show us how much reaction proceed in each direction, right? So for that matter, we define the equilibrium constant. And this is how we define it. You have the concentration of your product C to the power of its coefficient, multiply by concentration of your product D to the power of its reaction coefficient, divided by concentration of reactant A to the power of its coefficient, multiplied by concentration of B to the power of its coefficient. So in other words, basically what we wrote here. And then this is the sign that we use for like concentration. And here, C, D are your products, right? And then A, B are your here, B and A, your reactants, and then the small letter C, D, A, B are their coefficients. Does that make sense? And this is how we define that. Or like rather, the scientists made experiments in the laboratory and then they realized this is what gives us the equilibrium constant. Or like this is the most efficient way to define that. So what is concentration?
The amount of something.
The amount of something. What else? So if I say like, what is its unit? Is it like, so if it's amount of something, can it be kilogram?
No, it's a percentage.
Percentage? Okay. Yes?
Isn't it like how much of something per mole?
How much per mole? Yes. So all of you are giving like useful information for kind of like the complete definition. So concentration, if you go to the doctor and then they say that the concentration of the cholesterol in your body is too high, or like the sugar concentration in tea, right? So what is concentration? So as your friends mentioned, as I said, all of you guys said like useful information for me to tell this. So concentration would be like amount per unit of volume, right? So it can be like kilogram per cubic meter, right? Or it can be gram per liter. Or as your friend mentioned, we can report that as moles per liter. Or it can be like moles per cubic centimeter. I guess I have it like this. Okay, so that is concentration. Okay. So when we have like this type of reactions, this is how we define equilibrium constant. And I will write some questions to kind of like solve some numerical examples so this becomes more clear. But I asked you to remember the definition and just like what I wrote here, and then also study the book. And as I said, I also write here which section I'm teaching, so you have the chance to go and read it. Any questions? Yes?
Is it always like products divided by reactants?
Yes, so if you have like your equation written as this, yes, it would be always like this. Great question. And now, based on the value of equilibrium constant, we can see which direction the reaction is proceeding more, right? Because we have like writing AA plus BB in equilibrium with CC plus DD, but we don't exactly know that is it like reaction goes mostly left to right or right to left, or is it just not occurring anymore? Is it like in equilibrium? So the size of the equilibrium constant tells us which direction the reaction is favored. I call it kind of like this. So it's important to know that what does the reaction equilibrium is actually telling us. So just not reading what I wrote here. Remember, equilibrium constant is like concentration of D to the power of D multiplied by concentration of C to the power of C divided by concentration of A to the power of A multiplied by concentration of B to the power of B. So if I tell you this number is greater than 1, or in general, if I tell you this number is really, really big, right? Imagine like 1,000, just as an example. And then just numerically, what does it tell you? So if you have a ratio, that you divided two numbers, and now you got a really big number. So mathematically, what does it tell you?
The reactants were really small.
Exactly. You can say that reactance here is really small, or your products are really big, right? Or like both of them, mathematically, right? So now it means that if you have like C and D really big and these two really small, what does it tell you? Does your reaction proceed left to right or right to left? So left to right or right to left? Exactly, right? Because it should go this way, so you have like lots of C and D. So what is the opposite is correct. So imagine I have like the same thing, and I try to write it fast because I'm running out of time. So imagine you have this, and then this number is really small, something like near 0, imagine. So what does this tell you numerically? Yes, so whether this one is really big or this one is really small or both, right? So it means that this is here, A and B are really big. And then these are really small. So which direction reaction proceeds? Left to right or right to left? What's that?
Right to left.
Exactly. So if equilibrium constant is smaller than 1, the formation of A and B will be favored and the reaction proceeds from right to left. Okay? Question here before I proceed to the next lecture, next slide.
The first session, it doesn't change the equation if you go left to right and right to left, right?
What do you mean it doesn't? No, it doesn't. So your equation is like, do you mean this reaction or like this?
Well, anything that you wrote, it doesn't change whether you go right to left or left to right, so what's the point?
So
of
you have,
proceeding from left to right or right to left?
yes, but you want to study the reaction and know that what's happening so in the reaction. So chemically you're interested. So mathematically, yes, you just know if, you know, equilibrium constant is smaller than 1 or like bigger than 1. So in paper, it doesn't change the reaction itself, but you want to study this reaction and know which products you have more. So imagine you have like an industry and want to produce a specific compound, right? And then if reaction goes both ways and you want to produce like tons of a specific compound, and then that would be like D, right? That specific, you know, product. And then if the equilibrium constant is less than 1 or is really small, and then you get most of your reactants again, you cannot produce that much of the product that you wanted. So it's important to know this, you know, so in case you want to produce something or just like study the reactions, you know what's happening. Does that make sense? Great question. Any other questions? Okay. Any questions? Yes. Okay, so I wanted to talk about Le Chatelier law very briefly, but I think it's just more feasible that I bring the attendance and talk about it next class. Is the QR code working for everyone? Well,
It is very nice.
oh yeah. Thank you. Thank you.
I'm not walking out. Especially when I got oh. I'm hungry now.
Hello. I wanted to ask you, when we go home tutoring, are we supposed to ask the tutors to like email for our attendance?
You can do that, but I'm also going to get the names from Dale, so don't worry about it.
Okay, yeah, that's
He
what
said
I
he
was-
can tell me all, you know, the name of the students and how many sessions they went, so, yeah.
That's great. Thank you.
Thank you.
Have a good day.
You too.
Oops, sorry. Have a good day.
You too.